Walker could not prove his theories. His attempts to predict the Indian monsoon came to nothing. And he failed to connect what he'd learned about the atmosphere of the Pacific's west with the strange El Nino current of the ocean's east. Walker went to his grave in 1959, his ideas challenged or ignored. But within a decade, vindication. In the late 1960s, a Norwegian meteorologist, Jacob Bjerknes, bridged the Pacific Divide. He combined east and west, ocean and atmosphere, El Nino and southern oscillation.
The El Nino in the eastern part of the basin and the southern oscillation are put together to say that El Nino is really a basin-wide phenomenon. And it wasn't until after that that scientists started to take a closer interest. We've really only known about the phenomenon as a basin-wide or global impact phenomenon since the mid-1970s. That's 25 years or so. So there's a lot to learn, but there's a lot we know.
In normal years, there's a pool of warm surface water in the western Pacific, covering an area the size of the continental United States. This water is a vast reservoir of heat energy, some of which is transferred to the atmosphere. Hot, saturated air rises and is pushed by pressure differences to the east. When it arrives at the shores of South America, the air has become dry and cool. It descends to the surface and turns west again, forming the equatorial trade winds. Cool, too, is the ocean of the eastern Pacific, because the trade winds tend to push surface water away from the South American coastline. It's replaced from below by cold, nutrient-rich water, the upwelling phenomenon which supports the explosion of life off coastal Peru. During El Nino conditions, the equatorial Pacific is turned on its head. The westward flowing trade winds weaken, and sometimes they reverse. This allows the vast pool of warm water in the west to migrate to the central and eastern Pacific. Upwelling continues along the Peruvian coast, but the water coming to the surface is warmer and poorer in life-supporting nutrients. In one way, however, the waters are rich. The energy they contain triggers massive cloud formation, the monster El Nino storms which ravage the coastal desert. Typically, El Ninos last from 12 to 18 months. Eventually, the trade winds regain their strength, returning conditions to normal, and occasionally, conditions more pronounced than normal. These anti-El Nino periods have been dubbed La Nina events. La Nina meaning the girl child.
La Nina is viewed as normal, or an extreme case of normal. In some locations, normal heavy rains mean you're walking in the streets with water up to your knees. With a La Nina, an extreme case of normal, in quotes, maybe the water's up to your chest. You kind of expect it to be flooding, but you don't expect it to be severe flooding.
With phenomena like El Nino, generalizations can be dangerous because every Christmas child has unique characteristics. This we learned late in 1982 with the onset of an unusually powerful event. An El Nino which humbled an overconfident science community.
There was a meeting as late as October of 1982 in Princeton, New Jersey, where all the top forecasters were together, the researchers of El Nino. And at that moment in October, they said there would be no El Nino because they were enamored by one scientist's views about precursors. There must be these four conditions, and one or two of the four conditions was not present. So therefore, there can't be an El Nino.
It caught the community by surprise, and this was a shock. Our observing system capabilities were very primitive at the time. That El Nino was neither predicted nor was it even observed until it was nearly at its peak.
El Nino unexpected, the world unprepared, and as it turned out, at the worst possible time. The 82-83 event will long be remembered for the unusual severity of its teleconnections. The term used by meteorologists for the idea championed a century ago by Gilbert Walker.
A phenomenon in one part of the world affecting weather or climate in another part of the world. So, for example, El Nino, we know, is characterized by warming of the equatorial Pacific Ocean every few years. But it's also characterized by warmer and drier winters in the Pacific Northwest, wetter and colder winters along the Gulf Coast states of the U.S., rainfalls, heavy rains in western South America, drought in Australia and Indonesia. Those are teleconnection patterns that result from warm sea surface temperatures in the eastern and central equatorial Pacific.
But El Nino's teleconnections, the phenomenon's tentacles, reach far beyond the borders of the Pacific Ocean. In 1982-83, southern and sub-Saharan Africa were in deep drought, famine-producing drought. And on the Indian subcontinent, the life-giving monsoon failed. These distant teleconnections are some of the most disastrous and the most difficult to predict.
There are other things in the climate system that can affect weather variability, so that the further you get from the tropical Pacific, the weaker the link becomes between El Nino and weather in different parts of the world.
What was clear in the aftermath of 1982-83 was the need for revolution in the science of ENSO, the El Nino Southern Oscillation. A revolution in monitoring and forecasting. One solution came from the United States. The Tropical Atmosphere Ocean Project, the deployment of buoys heavy with sensors across the equatorial Pacific.